In this video, we're going to be looking at acceleration. So from the subject outline, students will understand that acceleration is a change in motion. Uniformly accelerated motion is described in terms of relationships between measurable scalar and vector quantities, including displacement, speed, velocity, and acceleration. So, first we're going to look at exactly what acceleration is. And very simply, acceleration can be defined as a change in motion. More specifically, a physics definition is that it can be defined as the change in velocity of a body over a given amount of time. So basically, things can either be, imagine when you're running, doing the 100-meter sprint, you are accelerating up to your top speed, you're increasing in speed or velocity. Things can also be decelerating, so you can be coming to a stop. So acceleration is a change in velocity over a given amount of time. And generally, if acceleration is positive, it means something is speeding up. And if acceleration is negative, it means that something is slowing down, it's decreasing in velocity over time. So here's a diagram. So as I just mentioned, something can be speeding up. So it's accelerating if it's increasing in velocity. Something can also be accelerating because it's slowing down. It's decreasing in velocity over a given amount of time. And lastly, we can actually, if something's moving at a constant speed but it's changing direction, it's actually accelerating as well because it's being displaced. It's changing directions. So those are the three cases of acceleration. So how do we calculate acceleration? So very simply put, it's the change in velocity, okay? So acceleration is the final velocity that you are moving at. Say I'm running. So if I wanted to measure the acceleration of me sprinting and reaching my max speed, in order to calculate the acceleration, it would be the final velocity, take the initial velocity, and then it would be divided by the amount of time taken. So, this is the formula you get on your formula sheet. A equals change in velocity over change in time. Now, very simply put, this change in velocity is the final velocity, which we're going to give a symbol of v, and this initial velocity, which we're going to give a symbol of v0, because initial means a time of 0, so the 0 is for a time of 0. So acceleration is a change in velocity, the difference between the final and the initial, over a given amount of time. So again, velocity or speed is going to be measured in meters per second. Same with initial velocity. And our time is we're going to need to make sure that's in seconds. And finally, the unit for acceleration is meters per second squared. So the reason being is the following. So velocity is a measure of, acceleration is a measure of change in velocity over a given amount of time. So the units for our top line of our acceleration formula is meters per second, and units for our denominator is seconds. So acceleration is really meters per second per second. So imagine I'm starting off at a speed I'm starting off at an initial speed of 0, and I reach a top speed of 10 meters per second, so a final velocity of 10 meters per second. So final velocity is 10, and my initial is 0, and it takes me 10 seconds, say it takes me 10 seconds. So 10 takes 0 is 10, 10 divided by 10 is 1. So what I am accelerating at is 1 meters per second for every 1 second travelled, until I reach a top speed of 10 meters per second. So the way that we would simplify the units of 1 meters per second is 1 meter per second squared, and we can simplify that using index notation to 1 meter s to the minus 2. So it doesn't matter which way you write it out of those two units, but that's how we get the units of meters per second squared. So, this is the formula that you're going to be given on your formula sheet. You need to be able to rearrange this to solve for all four variables from the last slide. So, acceleration is final velocity take the initial velocity over the amount of time taken. Now, so that's acceleration. Now you need to be able to rearrange this. So very simply put, the first one is, in order to solve for time, if you're trying to find time in a question, you can just swap a and t. So to solve for time, it's going to be time equals v final velocity take v naught over the acceleration. That's going to be the amount of time taken. In order to solve for, I'll solve for velocity first. So this equation here, now we want to get velocity by itself so we can use it to solve calculations. So the first thing we need to do is, we don't get rid of the the minus v naught. First we need to get rid of the denominator, so we're going to times both sides by t. Now I'll show you the working over here. So if we have acceleration equals final speed take initial speed over time times both sides by t, they'll cancel out and we'll be left with time times acceleration equals v take v naught. Lastly, we want to get v by itself, so this is v take v naught, so if we want to remove v naught from this side of the equation, we can plus v naught to both sides. We can plus v naught to both sides, and they'll cancel out, and we'll be left with v is equal to v naught plus a t. Now you don't have to rearrange it every time. This one's a really easy one to memorize, v equals v naught plus at, and it makes sense as well. So the final speed of an object is equal to its initial speed plus its acceleration for a certain amount of time. The last one is if we want to get v naught by itself. So I'm not gonna rearrange the entire thing. I'm just gonna start at this starting point, v equals v naught plus at. So if we want to get v naught by itself, we're actually going to have to take at from both sides of the equation, and then we'll end up with this v naught equals v, and then we're taking at from both sides, so it'll be v take at. So these are our four formulas that you need to be able to rearrange from the initial equation. You need to be able to get to these four forms of the equation. So make sure you get them down and have a bit of a practice trying to rearrange them to get to those four. So I'm just going to do a few quick examples now. The first example, so a car accelerates from a velocity of 10 meters per second to a velocity of 25 meters per second in 15 seconds. What's the acceleration of the car? Okay, so velocity of 10, so that's its initial velocity of 10 meters per second to a velocity, so that this second one's going to be our final velocity of 25 meters per second, and that's taken a time of 15 seconds, and we're trying to find acceleration. So acceleration is what we're trying to find. So acceleration is change in velocity, v take v naught over time. Substituting into our formula, we're going to have 25 take 10 over the amount of time taken, which is 15. So 25 take 10 is 15, 15 divided by 15 is 1, so it's 1 meters per second, or 1 meter per second squared. The next example we're going to look at is an athlete is running at a speed of 15 meters per second. If he comes to a stop in 2 seconds, what is his acceleration? So what do we know? Athlete's running at a speed of 5, so that's his initial speed. 5 meters per second. It comes to a stop in 2 seconds, so time is 2 seconds. What is its acceleration? So we've only got 3 bits of information. We've only got 2 bits of information and an unknown. What are we missing? If he comes to a stop. So if something's come to a stop, what's the final velocity going to be? It's going to be 0. So final velocity is going to be 0. So we're not explicitly given that in the question, but we can very easily work that out if we read it properly. So again, the same formula. Acceleration equals change in velocity, v take v naught over time. So and the final velocity is 0. Initial velocity was 5 over 2 seconds. So 0 take 5 is minus 5. Minus 5 divided by 2 is minus 2.5 meters per second meters per second squared. So this is why it's important to make sure you've got the right variables in the right spot, because now we have a negative. So we have negative 2.5 meters per second squared. So this athlete is actually decelerating. He's starting off at an initial speed of 5, and in 2 seconds he's coming to a stop. So every 1 second he's decelerating by 2.5 meters per second. Hope that makes sense. The last example I'm going to look at is a train accelerates at 2 meters per second squared, so acceleration is 2 meters per second squared for 30 seconds. If its initial velocity was 10 meters per second, so v equals 10 meters per second, calculate what the final velocity will be after 30 seconds. So we're trying to find final velocity. So from our previous page where we did the rearrangements, we have that v equals v naught plus at. So plugging it into our formula simply, we're going to start off at 10 meters per second, and then for every 30 seconds we're actually going to be accelerating at 2. So this formula does actually make sense. So if we're starting off at an initial speed of 10 meters per second, every 1 second we're increasing by 2. So if we're driving the train for 30 seconds, 2 times 30, so it would be 10 plus 60 is 70 meters per second. It's a bit hard for me to write on this drawing pad. That's meters per second. So I will now want you to move on to doing some practice problems, and they'll be outlined on the Google Classroom. Thanks.